Hello. Today we're going to talk about a very general framework for drawing variations of simple graphs that we know. We're going to apply this later in the video to quadratic functions, but we'll be using these exact same principles to draw all sorts of graphs throughout the entire course. Exponential, logarithmic, trigonometric, all sorts of stuff. But first of all, we need to take a function f, a simple prototype that we know how to draw the graph of, and we're going to alter it algebraically in certain ways and see if we can't draw the graph of something much more complicated. Well, if we take a look at what our new input, instead of it just being f of x, we've got this whole mess. I call this the heart of the function. Okay. We can talk about the effect of having a multiplier outside the function, outside the heart I should say, a multiplier inside the function, having an extra term outside the heart of the function, and having an extra term inside the heart of the function. Okay, the effect that all those different numbers will have on the shape of the graph. So step by step we can build up the graph of this very complicated function. So we start off with our graph of our very simple prototype, y equals f of x. Now, we think of the effects that each of these parameters has. Our c, what it's going to do, it's going to stretch the graph vertically by a factor of whatever c is. If c happens to be negative, it'll also reflect it about the x-axis. What's really happening here is all the y-coordinates of every point on the graph are going to get multiplied by c. After that, we're going to take a look at what our d value is. What's the multiplier inside the heart of the function? And we will compress the graph horizontally by a factor of d. If d happens to be negative, we'll reflect our graph about the y-axis. Essentially what we're doing is dividing all of the x-coordinates by d. Then afterwards, we will take a look at our term outside the heart of the function. And if a is positive, we'll shift our graph up that many units. If it's negative, we'll shift down that many units. And lastly, we'll take a look at our term inside the heart of the function. If b is positive, we'll shift to the right that many units. If it's negative, we'll shift to the left that many units. Now there's an important order to all of these. You must do them, really, you have to start with your basic prototype. Then you can do your stretches, compressions, reflections in whatever order you like, but they have to all happen next. And then after those are all done, the last things that happen are the shifts. Okay, that order is very important. Also notice the heart of the function. It's factored. So whenever you see a coefficient in front of your independent variable and you're trying to draw the graph, you must factor that coefficient. And we'll see examples of those later in the course. But let's see how all of this works. We'll use a completely abstract example, some totally made up function, but just see the effects that all these different numbers have on its shape. Okay, so we're going to start with an arbitrary f of x and do each one of these transformations. Okay. All right, so I'm just going to make something up here. It's completely arbitrary. So I'll make something kind of extreme. Maybe my graph looks like this. This y-intercept, let's say it's at 0, 2. Let's say this x-intercept here is at negative 2, 0. And this one over here is at 3, 0. All right. From there, if we apply our first transformation, we would have a vertical compression or a vertical stretch by a factor of a half. So it'll actually get shorter. So all our y-coordinates are going to get multiplied by a half. So there's y equals 1/2 f of x. I guess that means that the new y-intercept is going to be at 0, 1. Okay. Then the next thing we're going to do is apply this multiplier inside the heart of the function. So the negative there tells us that we should reflect the graph about the y-axis, and the third tells us that we want to stretch it out by a factor of 3. All our x values are going to be divided by a third. They're going to get multiplied by 3. Okay, so this is going to be a little bit tricky here. So this x-intercept here at -2 is going to get divided by -1/3. It's going to get multiplied by -3. So it's going to head on out there to 6. And the other x-intercept, it's going to get divided by -1/3. It's going to head out to -9. So let's see if we can make this all work here. So there we are. There's y equals 1/2 f of -1/3 x. I guess I don't need that bracket there. Okay. And the last thing we have to do, I usually do the shifts all in one shot because they're fairly simple. We're going to shift up. That's what the +4 tells us. And the +1 inside is going to be a shift to the left. Okay. So we're going to take that green graph and we're going to shift every point left 1 unit and up 4 units. Alright, so if we take a look, our new y-intercept is going to be up here at 5. A lot of the old interesting points will be down at 4, and everything's going to get shifted left by 1 unit. Okay, so if we take, for instance, the y-intercept, and we move it up 4 units and to the left 1, it would end up there. If we take this x-intercept out here, move it to the left 1 unit and up 4, it'll end up there. And this x-intercept, move it to the left 1 unit and up 4, it'll end up there. And that's our final graph. Now you can see the picture can get pretty cluttered pretty quick. Now the good news is when we apply this to quadratic functions, it'll be a little bit more clean and straightforward. So let's take a look at one of those examples. Now we've got a quadratic function here written in the completed square format. Now this is essential if we actually want to see the proper graph transformations. Okay, so that's one of the reasons why you need to complete the square. So if you have to, complete the square first. Now let's write a recipe as to what each of these things are going to do. We're going to start with our basic prototype. Start with y equals x squared. So that'll be the first graph we draw. And then the second graph we're going to draw, we'll deal with that -3 out front. So we'll deal with it in 2 steps. We're going to stretch vertically by a factor of 3. Our graph will get a lot taller. And then the fact that it's a -3, we're going to reflect about the x-axis. Okay. Now you notice that there's no coefficient inside the heart of the function in front of that x. There's just the bracket right there. And if you've completed your square properly, you'll never have one. So we don't need to worry about that quite yet. We will have some shifts though. We have that +2 inside the heart and a -1 outside. We'll do both those shifts at once since they're fairly straightforward to do. Of course, they have to happen at the end, so we're going to shift down 1 unit and left 2 units. All right. So there we've got our recipe. I expect you to write a recipe every time you do graph transformations, so I can see exactly what you're thinking. So we'll start with our basic prototype, the y equals x squared. If you recall from your previous courses, it's a parabola that looks like this. Okay. This should be memorized, that basic prototype. And you should put it in your graph prototypes page at the back of your book. So that's the first step. We drew y equals x squared. All right, let's move on to the next step now. We're going to stretch it vertically by a factor of 3, so it's going to become a lot taller. So all the y coordinates are going to get multiplied by 3. So that's y equals 3x squared. Next thing that happens in step 3 there, we reflect it about the x-axis. So we're going to take that blue graph and reflect it about the x-axis. That's y equals negative 3x squared. And lastly, we're going to take that green graph and shift it down 1 unit. So it looks like y equals negative 1 is going to be a new interesting y value. And left 2 units. So negative 2 is going to be a new interesting x value. So here's my new vertex at negative 2, negative 1. And our graph opens downwards there. And that's my final graph. Y equals negative 3, x plus 2 squared minus 1. And of course, if I asked you to give me the domain and range of that graph, you very easily could. If I asked you for the y-intercept, you just plug in x equals 0 into that expression. And if I asked you for the x-intercept, you could just set it equal to 0 and solve that quadratic equation the way we did when we were solving equations by completing the square. We'll, of course, do a lot of those things together in class. But for now, I'd just like you to understand how we can draw quadratic functions with graph transformations. Thank you.